You've probably used an AI model like ChatGPT or Gemini. It can feel like absolute magic, right? But the technology behind it is very, very real. And it all goes back to a single, groundbreaking paper that completely changed how machines understand language. So let's pull back the curtain and demystify the Transformer. So before 2017, even the most cutting-edge AI had a huge problem. Think about Google Translate back then. It had to read a sentence sequentially, just like you or I would, from the very first word to the very last. And this created a massive bottleneck.
But imagine for a second, what if you could just throw that rule out the window? What if an AI could look at every single word in a sentence at the exact same moment and grasp the entire context in a flash? Well, that simple question, that is the key to this entire revolution.
To really appreciate the breakthrough, we first have to understand the problem it solved. It's what we call the sequential bottleneck, and for decades, it was the #1 challenge for language AI. For years, the go-to approach was something called a recurrent neural network, or RNN. But the early ones had a terrible memory. In a long sentence, the information from the beginning would just kind of fade away by the end. It's a problem called the vanishing gradient. Then came LSTMs, which were a huge improvement, way better remembering things, and they led to the models that really dominated machine translation for a while.
But here's the thing, even the absolute best of these models had the same fundamental weakness. They processed information one chunk at a time, in a series, and this was a massive roadblock for two big reasons: speed and context.
And this slide just lays it out perfectly. The old way was sequential, and that meant it was slow. You just couldn't take advantage of the insane parallel processing power of modern GPUs. Plus, because the information had to pass down this long chain, it was easy to lose the context from the beginning of a sentence. The Transformer just flips the script entirely. It looks at everything at once, in parallel, which makes it blazing fast and perfect for modern hardware, all while keeping the full context intact.
Okay, so how did we make that jump? How did we get from that slow, one-word-at-a-time world to the powerhouse we have today? Well, it all started with one research paper and a frankly radical new idea. In June 2017, 8 researchers at Google published this paper, and the title, attention is all you need. That's pretty bold. Their big idea was to completely throw out that sequential, step-by-step processing and instead build a new architecture based only on a mechanism called attention. At the very heart of the Transformer is this idea of self-attention. The easiest way to think about it is as a system that lets every single word in a sentence look at every other word to figure out how important they are to each other. It doesn't just see the word it can instantly tell if it refers to the dog, the company, or the planet mentioned earlier in the paragraph. And it does this for every word all at the same time. Now, this sounds incredibly powerful, but how does it actually work under the hood? Let's take a peek inside and see how a transformer actually goes from your prompt to a generated response. The whole process really breaks down into 3 main stages. First, you've got to turn your text into numbers the computer can actually work with. Second, those numbers get processed through the core engine room, the transformer block. And finally, the model makes a prediction about what word should come next. Okay, so in stage 1, embedding, your prompt gets chopped up into pieces called tokens. Each token is then turned into a long list of numbers, a vector, that represents its meaning. But wait, if we're not processing in order, how does the model know the sequence of the words? Well, that's where a clever trick called positional encoding comes in. Another vector is basically added on, stamping each word with its position in the sentence. And now for the main event, the transformer block. This is the engine of the whole system. It's got that self-attention mechanism we talked about, plus another simple neural network to chew on the information a bit more. What's wild is that most modern LLMs are just dozens of these blocks stacked one on top of the other, each one building a richer and richer understanding of the text. So to really get self-attention, this web search analogy is just perfect. For every single token, the model creates 3 different vectors: a query, a key, and a value. Think of it like this. The query is the word you're currently focused on, your search term. The keys are like the titles or headlines of all the other words in the sentence. And the values? That's the actual content, the meaning of those other words. So, the model takes the query from one word and compares it to the keys of all the other words to see how well they match. A strong match gets a high attention score. Then, it uses those scores to create a new representation for our word, pulling in bits and pieces of the most relevant values from across the entire sentence. It's basically grabbing context from where it matters most. All right,
After the input is passed through all those transformer blocks, the model has this incredibly deep, contextualized understanding of what's going on. Now it just has to predict the next word. To do that, it produces a massive list of raw scores, called logits, one for every single word in its dictionary, representing how likely each one is to be the correct next word.
A final little step, called a softmax function, just cleans up those raw scores into nice, neat percentages that add up to 100%. So for a prompt like data visualization empowers users to, the model might calculate a 45% chance the next word is see, a 25% chance it's understand, and so on. Then it just picks a word based on those odds, and that's your output. Now this new architecture wasn't just some small, incremental improvement. No way! This was a fundamental paradigm shift that unlocked a level of scale and performance nobody thought was possible. It changed the entire field of AI. Forever. The impact was just immediate and massive. To put this in perspective, that original paper has now been cited by other researchers over 173,000 times. That makes it one of the most influential scientific papers, not just in AI, but of the entire 21st century. Period.
And people knew it was big right from the start. Even before it was officially published, one of the peer reviewers said it was already the talk of the community, and that everybody was scrambling to replicate the results. They knew this was a total game changer.
And here's the crucial takeaway. Nearly every major AI model you hear about today is built on this foundation. OpenAI's GPT series, Meta's Llama models, Google's Gemini, they are all transformers. And the architecture is so flexible it's now used for everything from generating images in DALL-E to predicting the structure of proteins with AlphaFold.
But, and this is a big but, this incredible power to learn from these vast oceans of data also created a whole new set of vulnerabilities. A new class of threats we're really only just beginning to understand.
Because you have to ask yourself, when a model is trained on terabytes of data scraped from the internet, what exactly has it learned? And maybe more importantly, what has it memorized?
This leads to a really serious privacy risk called training data extraction. Researchers have shown that it's actually possible to craft special prompts that can trick a large language model into spitting out sensitive data it saw during training, word for word. We're talking personal info, copyrighted material, secret company code, anything it was trained on.
This stuff is so serious that security professionals are now building entire frameworks, like the industry standard MITRE Atlas, just to map out these new AI-specific threats. This covers things like prompt injection, where you trick the model into ignoring its own safety rules, or even training data poisoning, where an attacker secretly inserts bad data to create a hidden backdoor. These are huge areas of research right now. So while the Transformer absolutely solved a massive computational problem and kicked off the AI boom we're living through, it's also left us with a brand new challenge. We've built these incredible models that can understand and create language at a scale we've never seen before, but securing them and making sure they protect our private data, that's a problem we are still racing to solve.